flexural vibration. I bend it and leave it, then it has certain natural frequency. I want to measure the fundamental frequency for the bending moment and the overtones. So I will now talk to you about the theory of flexural vibration at the bar. What is the differential equation is satisfied? What is the boundary condition? And then I will tell you. Experiment is very simple. So any isotropic solid, isotropic means the property is the same in all directions. So if I take a single crystal of copper, the elastic properties are not the same in all directions. It is not isotropic. But if I make a powder of grains of copper and then I press them to make a bar, here for example, there will be individual grains of copper, but they are oriented at random. So in one grain, if you send an elastic wave, it may go along 1, 0, 0. In the next grain, it may go in some other direction. So for this material, which is granular and contains many grains with all orientations, you will get average value of the elastic constant, which is independent of direction. So it will be isotropic provided the material is a polycrystalline material. If you take glass, it is isotropic. You will get same value for elastic constant. So these are polycrystalline materials, so they will behave in an isotropic fashion. So for such isotropic materials, there are 4 moduli of elasticity you can define. The X modulus, you take the length of the material, you increase the length by applying a longitudinal stress, then you find what is the longitudinal stress by longitudinal strain, that is the X modulus. The next one is the shear modulus. Here you take a material, it may be a cube, then you apply a shearing force. The cube will become a parallelepiped, the angle will change from 90 degrees, that is the shear strain. And what is the force that you apply to produce the shear strain? Take the ratio, that is the shear modulus. Shear modulus will be less than the X modulus for all materials. Then you have the bulk modulus. The bulk modulus is I take the cube, put it in a liquid and apply hydrostatic pressure. The cube will shrink in volume in all directions. It will remain a cube, but the size will decrease. So find out what is the change in volume to the original volume. That is the strain that you are producing. Find out what is the pressure that you are applying. Then take the ratio of the pressure to the strain. That gives you the bulk modulus. And finally, the Poisson's ratio. To extend a material in this direction, it will contract in this direction. So contraction in the perpendicular direction by extension in the longitudinal direction. That ratio is the Poisson's constant. But all these 4 moduli are not independent. There are only 2 independent elastic constants for an isotropic material. If you take a triclinic crystal, which is the most anisotropic crystal symmetry that you can have, there will be 21 elastic constants. If you come to a cubic material, a single crystal of copper, there will be 3 independent elastic constants. But if you take polycrystalline copper, with copper oriented in all directions, there will be only 2 independent elastic constants. you can choose any 2 out of the 4 as the independent modulus. So you can choose generally the X modulus and the shear modulus, or the bulk modulus and the shear modulus are chosen as independent constants. Then the other moduli, the other 2 can be written in terms of the 2 independent moduli. So to know the full elastic behavior of an isotropic material, you have to measure only 2 independent elastic constants. Now I take a bar. This is a rectangular bar. This is the length. This is the breadth. And this is the thickness. This is the width. So I call this as the length. This as the width W. And this thickness or width B. And this thickness I call as D. Thickness is D. Breadth is D. Length is L. I take such a bar. I clamp it at one end. I clamp this between screws at one end. The other end is free. Now I bend this bar. So when the bar is not bent, the cross section of the bar is rectangular like AB, A dash, B dash. But when you bend it, A dash goes to A dash. And A dash goes to this point and B dash comes to this point. So when I bend this bar like this, you will see that it has moved from this straight portion. So in this bar, which has a thickness D, there is a plane at the midpoint, mid section. So if this is 0 and this is D, the plane at D by 2 will not undergo any change in length when you bend it. This is called the neutral plane. So the neutral plane is the plane in the bar which will not undergo any change in length when you give small deformation to the bar. So if this is the neutral plane, and you have bent it, it is curved, but its length is the same as the original length when it was straight. Points to one side will be elongated, points to the other side of the neutral section will be compressed. Now we want to find out what is the strain when the bar is bent and the radius of curvature at the point where you want to measure the strain is R. So you take a small section of the bar, take a small section of the bar. So this is the section before bending and this is the section after bending. This is the neutral plane, and this will be the so this is the line. This line and dash is in the neutral plane. Thickness is in this direction. Okay. So this line and dash will now be bent, but has the same length as the original and dash. Now, this end AB is perpendicular. So you extend them, they will be at one point O, and ON is the radius of curvature of this small element when it is bent. ON is the radius of curvature. Now take a point at the height y above the line. That means take a line like this. This height is y. So if this angle, if n and dash subtends an angle theta, then the length of this line will be r plus y into theta. So a line at a height y above the neutral plane will have a length r plus y into theta, where r is the radius of curvature of the neutral line. What was the original length when it was rectangular? Same as n and that. So original length is r theta. The new length is r plus y into theta. So original length. And length after deformation is r plus y. So what is the increase in length by original length? The increase in length delta L by L. R plus y theta minus r theta. So y theta by r theta. That is y by r. So the longitudinal stride of a filament at a height y above the neutral line is y by r. Y is positive above the neutral line, negative below the neutral line. So all lines above the neutral line are extended, all lines below the neutral line are contracted. Now if you give very small displacements, then the radius of curvature r, 1 by r, can be written as d square y by dx square. This is the y value as a function of x will keep changing. So this will be, this is a curve, y against x. So d square y by dx square is the curvature of the curve. You can neglect the term 1 plus dy by dx power whole square power sub 3 by 2. The dy by dx whole square can be neglected because we are considering small deformations. So we see that at any point at a height y, it is y by r, where 1 by r is d square y by dx square, y as a function of x for this curve. Now, you take a plane like this, then all the lines above the neutral line are extended, so you remove the material at the right, at that cross section there will be tensile forces. The forces above and under in this cross section, due to the rest of the bar, you bend the bar. The right side, you take any section, the right side of the bar is exerting a tensile strength on the elements to the left of this section. So you can remove the right side and replace it by a tensile force when y is positive and a compressive force when y is negative. So if you look at this cross section, at this section, look at this section, then at this section, this will be the intersection of the neutral plane. You take a small area dA at a height y above, there will be a tensile force T, which will be equal to the x modulus into strain at the height y. So this longitudinal tensile force T will be a function of y, and that is the force per unit area. Stress, the tensile stress Ty will be equal to y by r into the x modulus capital Y. X modulus into strain is the stress. T. Stress is force per unit area. So you consider a small unit area ds, force will be T into ds. So all these areas will experience a tensile stress, all these areas will experience a compressive stress. So you can, this will be, you take the cross section, this top of the cross section is pulled to the right, bottom of the cross section is pushed to the left. That means there is a bending moment about the neutral line, neutral plane acting on this cross section. There is a cross section, there is half, the top half is pulled to the right, bottom half is pushed to the right, therefore there is a bending moment. This bending moment will be given by because the strain is only a function of y. You take along the breadth, you take a height y dy, you take a rectangular section, a width dy, height y above the neutral line. At a very point on this rectangular strip, strain is the same because the all points are at a height y above the neutral line. Therefore, the force on this area will be the breadth B, this is the breadth B, this is along the height, so it will be B dy will be the B is the breadth, dy is the height, so the area of the strip is B dy, force is y into Young's modulus into y by r, and what is the bending moment above the neutral line? Force multiplied by the perpendicular distance from the neutral line. That distance is y, so into y. This is the bending moment due to this rectangular strip. You want to calculate the total bending moment. Total bending moment will be integral of this from one end of the thickness minus d by 2 to the other end plus d by 2. This is the bending moment at that cross section. And therefore you get this is B by R into Y into integral y square dy from minus d by 2 to plus d by 2. So this will be y the Young's modulus into b d cube by 12 for a rod of rectangular cross section into 1 by r. Where r is the radius of curvature of the neutral line. Now take, if r is the same at every point along the length, then you say you have uniform bending. So if the bar is so long, at every point along the bar r is the same, that is after bending the bar is part of a circle of radius r, you say uniform bending. You achieve uniform bending by putting the bar and two knife edges, putting a weight at the center. That is uniform bending. If you clamp the bar and apply a load, it is non-uniform bending. At different points along the leg, R will be different. Radius of curvature will be different. So suppose you take such a non-uniform bending, and take two sections, a small length like this, remove the left-hand part of the bar, replace it by tensile and compressive forces. Therefore, for the left-hand part of the bar, this will be like this. For the right-hand part of the bar, this will be like this. So the bending moment due to this will be opposite to the bending moment due to the other, on the other side of the bar. So suppose here the bending moment is YBD cube into 1 by R. It is YBD cube into 1 by R at a point X along the length of the bar. The other section is just at X plus X. If it is non-uniform bending, R will be different at X plus X. So it will be 1 by R into X plus X minus 1 by R into X. That will be the net bending moment on this small element. Because the two couples are not equal, then it is not uniform bending. You can write 1 by R at X plus dx as 1 by R at X plus d by dx as 1 by R at X into dx minus 1 by R at X. So you see that 1 by R at X will cancel out. 1 by R is d square y by dx square. D by dx of d square y by dx square is d cube y by dx cube. So the net bending moment on this small element is proportional to the length of the element. So I give you two forces, F, separated by a distance dx. What is the net bending moment? F dx. So we can say that the force in non-uniform bending, force at a point X will be y d cubed by 12 is to d cubed y by dx cubed. Bending moment is d square y by dx square and this is d cubed y by dx cubed. So we can replace all the torque by two forces. One force turning it this way, another force turning it this way. So you have a couple on this. Now I want the vibration of the bar. The vibration of the bar means I take a small length of the bar, it is vibrating along y. So it has an acceleration. Acceleration will be d square y by dt square. So if the two forces are equal, there will be one force is up, one force is down, net force will be 0. There must be a differential force which causes the bar to vibrate. When the bar goes away, there is a restoring force. To calculate the restoring force, you have to take what is the force at x, what is the force at x plus dx. So force at x is this, force at x plus dx will be force at x plus df by dx. So you will get d cube y, d power 4 y by dx power 4 into dx. And then you have to equate to the mass into acceleration of that small element. So when you do that, you get this equation for the vibration. Y is the displacement. You displace y, leave it. This is, you take a small length dx, the volume is V into d into dx. Mass is rho into b into d into dx. Mass into acceleration is this term multiplied by dx. And the restoring force is this term multiplied by dx. Dx and dx will cancel out. So this is the partial differential equation satisfied by the vibrating bar. You must note that the derivative with respect to x is the fourth power. The derivative with respect to t is second power. If you take a sonometer y, mass per unit length is m, then the equation is m d square y by dt square is t d square y by dx square. For a sonometer y, the x derivative is also second order, time derivative is also second order. But in a bar, the x derivative is fourth order, time derivative is second order. So this term will be dimension d square y by dt square will be length by time square. dy by dt is length by time. D square y by dt square is length by time square. Displacement by time square. And this term is displacement divided by length power 4. So 1 by period square must be proportional to, this is y by period square must be proportional to y by length power 4. Because it is a fourth order differential equation. So you will see that 1 by t square will be proportional to 1 by L power 4, or the frequency which is 1 by t. 1 by t is the frequency which will be proportional to 1 by square of the length of the bar. For a sonometer wire, frequency is inversely proportional to the length. Here it is inversely proportional to the square of the length. You will verify this fact. Second thing is, now I must solve this equation, and I can solve it by making a substitution. Alpha power 4 is 12 rho by yt square. The equation reduces to this form. You write the space part of the displacement, there is a time part which varies with the frequency t. We use the variable separable method, separate the variables t and x, solve for the space part of the displacement. So that is a fourth order differential equation. D power 4 y by dx power 4 plus alpha power 4 u is 0. It will have 4 independent solutions. E power alpha x, e power minus alpha x, e power I alpha x, e power minus I alpha x. These are the 4 solutions which will satisfy this equation. So a general solution is a combination of the 4. So the general solution will be, I take, instead of e power alpha x, e power minus alpha x, I take cos hyperbolic cosine alpha x, hyperbolic sine alpha x, and instead of e power I alpha x minus I alpha x, I take cos alpha x sine alpha x. This is the general solution. To find, we have to find the constants A, B, C, D by applying the boundary condition. Now where it is fixed, there is no displacement. Y is 0 at all time, at x is 0. That is one boundary condition. Second boundary condition is the tangent at this point is horizontal when you bend it. Where it is tangent is horizontal. So dy by dx is 0 at x is 0. At the other end, you are not applying any force, it is free vibration. So force is 0, d cubed by dx cubed will be 0, and bending moment is 0, d square y by dx square is 0. So these are the 4 boundary conditions. So the boundary conditions are u is 0 and du by dx is 0 at the black plane, and at x is L, the bending moment is 0 and the force is 0. You are not applying the force. Whatever force comes from the restoring force due to the elastic property of the solid. If I apply a force and make it oscillate, then I have to put a different condition here. Okay. Now you must solve for A, B, C, D using these conditions. And the solution is, you won't get a solution for all values of alpha. You will get a solution only for those values of alpha for which minus cos alpha L is 1 by hyperbolic cos alpha L. If alpha satisfies this condition, then you will get a solution. And you can see that alpha is related to the 12 rho by yt square into, there should be the omega square. I have omitted that omega square here. When you substitute for b square by dt square, you will get minus omega square rho bd. So this rho will be multiplied by omega square. Alpha power 4 will be proportional to omega square. So if I say only for certain values of alpha you have a solution, it means only certain frequencies are possible for natural vibration. Rho, Bd are all properties of the given part. The natural frequencies are given by the values of alpha which satisfy the boundary conditions. To find the values of alpha, you make a graph. This graph is not come out, not seen well. So cos alpha L is minus cos alpha. That is the condition 1 by cos alpha or minus hyperbolic secant alpha L. So if you have alpha L like, and you plot a graph, the secant h of x is 1 by cos x, therefore it is 2 by e power x minus e power minus x. When x is 0, the denominator e power x plus e power minus x. When x is 0, the denominator is 2, so secant x will be 1. When x is infinity, this will be 0, this will be infinite, so secant x will go to 0. So it will decrease as x increases, it will decrease from 1 to 0 monotonically. And we have to plot minus secant x. So I draw a graph, image, the next I take my y is y1 is secant minus secant x. So it will start at minus 1 and then it will exponentially approach 0. So this will be the graph y1 is minus secant x. The right side is cos x. Cos x will be 1, then it will go to 0, it will go up, it is an oscillating function. So this is y2 cos x. So where the two curves intersect, those are the values of x for which cos x is minus secant hx. So you can find those values, and these values are, the first value is 1.875. My x is alpha L, first value of alpha 1 L is 1.875. The next value, alpha 2L, is 4. There is a third value, there is the second value around 4.9, which I have mentioned in my manual. There is a third value. Alpha is proportional to, alpha power 4 is proportional to omega square. So alpha square is proportional to omega. So you write alpha 1 square L square is 1.875 whole square. Alpha 1 square is omega square into 12 rho by yd square. That's a constant for the given part. So that into omega square into L square is 1.875 square. So you can find what is the frequency mu1. So this is the first frequency, the lowest frequency for the bar. This is inversely proportional to L square. For a string, mu1 is inversely proportional to L. The second one is at 4 point something by 1.875 whole square, not 7.875. That is the third form. So that is about 6.22 times mu1. You have the fundamental overtone. For a string, the overtones are in the ratio of the integers. The fundamental is omega 1. The next higher frequency is 2 omega 1. Here, next higher frequency is 6.22 omega 1. And the higher frequency still is much larger. Frequencies are not in the ratio 1:2:3. So there are two things, frequency inversely proportional to square root. And the second, the overtone to the fundamental is 6.22. You will verify both and then calculate the x modulus. So here I can clamp this bar, I can open the screw, move the bar, clamp it so that any length projects outside. So I can start with a length of whatever you want, 150 millimeters, 200 millimeters. I am going to set it into forced oscillation. That means I am going to apply a force. But I will find the natural frequency, because of the forcing frequency, not just the natural frequency, you will get the maximum amplitude. So I will change the forcing frequency, find out at what frequency I get the maximum amplitude. That is the natural frequency for the vibrating bar. To force it, I have a small magnet at this end, and this is an electromagnet. There is an iron, and at that there is a coil. This can be loosened and moved along the bar, so that when you change the length, you can move it so that it comes across the magnet. So it will exert a force, attractive and repulsive force. But you must remember, because this has an iron core, the magnetic field produced by it does not vary linearly with the current. So the magnetic field produced by it will have terms B as a function of T. We'll have one term alpha 1, I will call it A1 I sin omega t plus A2 I sin 2 omega t plus A3 sin 3 omega t plus etc. A1 has the largest value, A2 will be smaller, A3 will be smaller. So the bar is forced at different frequencies. Omega 1, a smaller force at 2 omega 1, still smaller force at 3 omega 1. Bar will resonate when any of these components equals omega naught, the natural frequency. So you will get maximum amplitude when omega is omega naught, 2 omega is omega naught. As I change the frequency, you will get resonance. First, I start with a very high frequency. Suppose omega naught is 30 Hz. I start at 50 Hz. There will be vibration but small amplitude. I reduce the frequency. So from 50 as I reduce the frequency, when I come to 30, I will get the first resonance, and that will have a very large amplitude. Then I lower it further. When I come to 50, I will get the second resonance. 2 into 50 is 30. So I will get a resonance at omega naught by 2. I will get a resonance at omega naught by 3. So to find the resonance frequency, start at a very high frequency, close to 100 Hz. Reduce the frequency slowly. When you get the first resonance, that is the omega naught. You will get the second resonance, then note the frequency multiplied by 2. Okay? But to note the resonance, you start at the highest frequency, lower the frequency, see when you get the first resonance. Then you change then you see when the first resonance occurs, the amplitude will be so large, this will go and hit it. So I have a provision for moving this back. So you move it back so that the force becomes smaller. So at resonance, the amplitude is not, you can see the resonance, but it won't go and hit the. After noting the fundamental, I must note the overtone. Overtone is 6.22 times the fundamental. Force required to produce a displacement at a frequency omega is proportional to omega square. So at 6.22 times the frequency, I have to apply 36 times the force to produce the same displacement. I can't increase the current 36 times, but I can bring this closer so that the force increases. So I move it closer. But even so, I can't increase the force 36 times. I can increase it maybe 3-4 times. Now, keep your signal generator frequency around 7 times whatever frequency you found for the fundamental. Suppose the fundamental was 30. Keep to find the overtone. Start with 210 and 240 and lower the frequency. Then, if you look from the top, you can see it vibrating. The vibration adds the resonance, but amplitude will be off. If you place your hand here, you will see the vibration. So as you are reducing the frequency, you will see maximum vibration at one frequency, and then the feeling dies down, not that frequency. That will be roughly 6.22 times the fundamental. Then change the length, reduce the length, repeat it, do it for 5 or 6 lengths, and then plot a graph of square of the length in meter square against 1 by f. You will get a straight line. Find the slope. This slope, from this slope, you can calculate the x modulus, because the x modulus is 4 pi square by 1.875 power 4, 12 times density of brass. which are given in the manual, divided by square of the thickness of the bar, that's also given in the manual, multiplied by slope square. So calculate the x modulus and get the ratio f2 by f1 for the different length. Take the average value, which should be close to 6.22. You may get a value 6.5, 6.4, that's okay. So what this experiment tells you is how to measure x modulus by a dynamic method. Why is the dynamic method important? Measurement of frequency is always much more accurate than measurement of displacement. You take uniform bending, you load, you have a traveling microscope, you have a pin, and you say how much the pin is depressed. Measurement of frequency is much more accurate. Even when you apply very small load, your depth will be very small. You can't measure it very accurately. But resonant frequency, you can measure very accurately. So a dynamic method is always the preferred method for measuring elastic constant. It is widely used in research. You can prepare materials called metallic glasses in the form of thin film. You heat the metal to a very high temperature, cool it very rapidly. It forms a metallic glass. You can make thin ribbons of the metallic glass. You want to study the elastic property, then you use this technique. You put the strip. The experiment is more complicated. To determine resonance is more complicated. But the principle is exactly the same. You change the frequency and find the new resonance. So this is the preferred method used in research and most accurate method for measuring elastic constant. And very easy method to do because there is nothing you have to only know the change the length, note the frequency, and keep the amplitude.
So the resonance is identified visually? The resonance is identified visually?
Yes. In fact, the fundamental, the amplitude is so large. I told you, it goes and hits this. So the displacement, so much. At the second harmonic displacement will be the
one could also measure the current and you see the current should increase with the resonance.
Yeah, if you are measuring the current in your coil, then the current should increase. But you can visually see, so it is very easy to give in a college. The students can visually see the resonance, but you can measure the change in impedance of the coil at resonance.
That can be actually another experiment.
Can be done, but it will be, I can do it provided I have an air core coil. Then it will be easier. But the force exerted when air core coil is smaller because of the extent. So this is a very simple technique, but very effective technique for measuring X modulus. And people have done when they have got slopes. If I say 0.59, people have got values like 0.5255. So you will get slope which agrees with the values I have given.
So does damping affect the calculation?
Yeah, wait. See, I am deaf, completely deaf here, going deaf. So I have to come to you if you ask me a question.
So I'm asking, does damping affect the calculation?
Yes. You see, here there will be damping. It is, if you have no damping, then the resonance amplitude should become infinite, but there will be damping. To measure the damping effect, what you can do is, you can set it in oscillation, switch off the current, and see how the vibration amplitude reduces as a function of time. Then you can measure the damping effect. In fact, in research, measurement of damping is one of the important things that are done. In mechanics, we have only 2 experiments, this and rigidity modulus. Because I thought viscosity you measure by capillary flow. I think people do it in B.Sc. Surface tension you measure by capillary rise. So I thought these are simple enough experiments. So in mechanics I have only 2 experiments, this and torsional vibrations of a ball wire. Surface tension you can measure by liquids, that I will set it up